Hello everyone, my name is Baoming Yan from Alibaba Group. Today, I will briefly introduce our technical solution of the recent Evoked Expression from Videos challenge. The title of our method is Multi-Granularity Network with Modal Attention for Dense Affective Understanding. Affective understanding is a task that aims to predict the viewer's expression invoked by the videos, which could be applied to video creation and recommendation. In the recent EEV challenge, a dense affective understanding task is proposed and requires frame-level affective prediction. As shown in this table, there are almost 5,000 videos corresponding to 3,370 hours are provided. 8 million frames are annotated with 15 viewer expressions. Each expression ranges from 0 to 1 in each frame, corresponding to the confidence that the expression is presented. The expression of each frame in the test set is required to predict, and the evaluation score is the average correlation of each expression across the video frames. For this dense prediction task, we consider that the expression of the specific frame could be determined by the signals of various time scales, and we should employ multi-granularity features for better description of the target frame. Hence, we extract the multi-granularity features for each video. The multi-granularity features could be divided into 3 levels. It's a frame level feature, clips level feature, and video level feature. This multi-granularity and multimodal feature then fed into the modal attention fusion model to fuse the various features into a global feature. Then we use a MOE mixture of experts classifier for expression prediction. This is a detailed description of the multi-granularity features. The frame level feature contains image features and audio features. For image features, we use Inception ResNet v2 pre-trained on ImageNet to extract this feature. This feature may contain visual silent content of the frames. Audio feature is extracted by VGG style model provided by audio set on preliminary vision of YouTube ATM. The audio style information could be extracted. And the clips level feature represents semantic context information around the frame. For example, human behaviors, semantic information from speech. S3D CNN backbone is used to extract features for human behaviors. The S3D backbone is trained by self-supervised information between visual content and speech text on how to 100M dataset. We also download the subtitles of the videos and find the nearest speech text for each frame. Then a pre-trained BERT model is used to extract the feature. The video level feature consists of the main affective information related to the theme of the video. We train a video level expression prediction network on the EEV dataset. The video level expression is obtained by the averaged labels of frames. The output of the last hidden layer of the model is used. The modal attention fusion model is proposed to emphasize more affection-relevant features. We first contented the above multi-granularity multimodal features and predict the weight of each feature. Then the weights are used to emphasize more relevant features. And some features may be missing in the video. We use model level dropout to make the model robust. A 3 experts MOE model is used for expression classification, and we use BCE loss to train all the parameters in our model. This is the experiment part. To evaluate the importance of different granularity of features, we start with frame level features and gradually add the clip level features and video level features. The experiment results on test set of the EEV distance are shown in this the left table. For the frame level feature, the performance of image feature and auto feature is evaluated separately. We could see that auto is more effective than visual content for effective on prediction. And the combination of image and auto feature could further increase the performance. And after the introduction of clip level features, the correlation score is remarkably improved. This indicates the importance of semantic context information around the frame. It is noted that the subtitle features are more effective than spatial temporal features. This means more semantic information exists in the subtitles. And the introduction of video level features further increased the performance and proves that the importance of the effective information from the whole video. We further evaluate the performance of model fusion and the classification model. MOE is more effective than MLP, and our model attention fusion is more effective than the concatenate operation. We use ensemble methods to achieve better results. For the dense affective understanding task, our method has two contributions. The first is multi-granularity feature construction. The model could learn more semantic context and video theme information. The second is model attention fusion, and the model could emphasize more affection-relevant features. That's all. Thank you.